Hi, my name's Zach Horton. I'm a PhD student in the statistics department at UC Santa Cruz, and I'm excited to share a bit of my research with you. Suppose for a minute that you find yourself experiencing a large earthquake. Hopefully you and the people nearby are safe. Once the tremors stop, one question looms above all else. Is it over? When is the next earthquake? Questions about events occurring repeatedly over time fall under the umbrella of recurrent event modeling, which is my area of research. It focuses on building models and distributions on what are called the inter-arrival times, or the time elapsing between events. The simplest model for inter-arrival times would be to assume that each inter-arrival time is independent and arises from the same distribution. This plot shows some examples of simple choices for the inter-arrival distribution. Of course, simplicity is rarely the case in the real world. A common way to get more complicated distributions is to use a mixture model. By combining several simple shapes together, we can create more complex distributions, like those seen here. However, not all shapes are reasonable. Take a look at this data set, showing inter-arrival times of large earthquakes since 1900, split across 4 regions of the Western Hemisphere. A distinct feature for each is that the shape appears to be decreasing. So inspired by this earthquake data, the question that we sought to answer was this: can we build a mixture model that is constrained to produce only decreasing shapes and yet is still flexible within that constraint? The answer hinges upon a mathematical result shown here. It says that any decreasing function, say g of x, can be represented as an infinite mixture of uniform or flat distributions, where the weighting is done according to some function g star, such as in this example. In other words, a big enough mixture of uniform blocks can represent any decreasing shape. Using that result, in combination with a powerful framework called the Dirichlet process mixture model, we were able to produce a framework that not only met our shape goals, but remained computationally feasible as well. Now, what's more interesting are the results we obtained from applying our model to the earthquake data. On the top row, we see that our objectives have indeed been met. All the shapes are decreasing, yet flexible, and overfit doesn't appear to be an issue. We've also included a curve known as the K function on the second row. In short, the K function measures how clustered events appear. Our finding here is that earthquake cluster behavior differs across regions. Specifically, regions near the equator exhibit stronger clustering behavior. This suggests that aftershocks may be more prevalent in those regions, which is useful information when, say, designing large buildings. We're excited by the method that we've designed, and we expect that it can have a big impact in analyzing recurrent event patterns within this decreasing shape framework. Thank you for listening.